Hello, everyone. Welcome back to the second part of this discussion about a new linear programming hierarchy that's complete for linear codes. And in the first part, we have introduced the hierarchy. We have explained how it fits in with existing hierarchies and what was our goal in designing this hierarchy. And we stated two results about this hierarchy. The first one is that for general codes, we cannot impose a lot of constraints, and the hierarchy collapses. It's equivalent to any level of the hierarchy is equivalent to those arts, original linear programs. And the second result is that for linear codes, as you go to a sufficiently high level, you get exact completeness, right? It's a hierarchy that the first level is the same as the Delsart, and as you move at a sufficiently high level, you have a guarantee that you're going to be very close to the correct value, the correct size of an optimal code, so it's complete in this sense. All right, so let's quick recap the definition of the hierarchy. And it was based on this notion of L-point interaction. So similar to sum of squares, that's an L-point bound, an L-point interaction. We, we generalize this notion of weight distribution to the notion of a weight configuration. So in the weight distribution would record the distribution of distances or the distribution of Hamming weights for linear codes. And for a configuration, what we're going to do, we are going to look at tuples of code words, or more generally here, words, and you're going to consider the span of the tuple. And they're going to check the Hamming weights in the span. So here you're given this tuple of words. And then for every subset of L, you're going to check what is the Hamming weight that we see, right? And that's going to be quite useful for linear codes because we know that everything in the span, if this is a tuple of code words, everything in the span is also a code word. And then we know that it needs to satisfy the minimum distance of the code. All right, so this is going to be a configuration. A configuration is just a function from subsets of L telling us what is the Hamming weight that we should see, right? So here we had this small typo. So when I mentioned 1, 2 here, this is 2, 3, right? 2, 3, let me correct this, 2, 3. All right, so and then with this notion of configuration, we can actually pass through to the distribution, the L configuration distribution of the code, and that's going to be just the collection or overall configurations, as in the previous case. So very good, we have this, and we saw that we can generalize McWilliams identities, right? And then in fact, McWilliams inequalities. So we proved the McWilliams identities. And when L equals to 1, we have the usual notion of the Krochuk polynomial, and it also generalizes, right? So it's a Fourier transform, now not of a given Hamming weight I, but it's a Fourier transform of the indicator of a given configuration. So it's more general. In the past, it was just the sphere, but now it's this potentially more complicated looking set, which is okay, very good. And then we proved the higher order McWilliams identities. Well, we stated that it holds in general for if you generalize this appropriately for general codes. And very good. And with this, as in the case of Delsarte, we can give a relaxation, right? The relaxation, you're going to take the max overall, such you're going to sum the weight distribution. Here you would expect, instead of seeing the size of the code, you would expect to see the size of the code to the L, right? At least for integral solutions, size of the code to the L. We have a normalization constraint. Since the AH, they are counting, they should be non-negative. We have, as before, the Krochuk transform, right? But those are higher order Krochuks indexed by configurations this time. And we also have the distance requirements, right? So whenever a configuration is saying that some vector has a small Hamming weight, and here you need to specialize whether you're working with linear codes or not, because for linear codes you can impose a lot of constraints, and that's great. And for nonlinear codes, this forbidden set is much smaller, right? So for linear codes, you can impose that whenever there's a subset, such that the Hamming weight is violated, you put this in the forbidden configuration. Whereas here, for general codes, you can only impose for singletons, right? Very good. So overall, what we had is that very similarly looking program to Delsart, right? At least to me, synthetically, it resembles a lot, and it's a hierarchy that we can choose. L equals 1 is exactly Delsart, and it would be extremely nice to see an analysis, a theoretical analysis of L equals to 2, 3, and so on, right? And what we are left to prove, so you have two things that we stated. The first one is collapse. Collapse is not very hard to prove, so and I think that the completeness is the more interesting result, and potentially the one that we are going to prove here. And to show the completeness is also not hard, but it's very curious because just by looking at this linear program, it's at least even to this day, it's not obvious at all that we should have completeness, right? From these linear constraints. And the way that we're going to prove completeness is from an equivalent perspective. So we have seen, and that's why you covered, we have seen that the Delsartes linear program is equivalent to theta prime, right, on a suitable graph. And the same thing is going to happen here. So this hierarchy that we have can be seen as the theta prime on suitable families of graphs. So you have a family of graphs that becomes larger and larger. It's going to depend on n and d and l, right? And if you look at the theta prime on those exclusion graphs, that version of theta prime is equivalent to this one. But the nice thing about theta prime is that it's more human and understandable. It's something that has more intuition. And from that perspective, we'll be able to prove completeness. Okay, so let's go back. So in order to prove completeness, you would need to establish some equivalence. And we can create families of graphs, right? I don't know. So suppose that we have some configuration. That's a configuration. Let me index some parameters here. So we have n, we have some distance d, and we have some level L. Very good. So we have this configuration, and we can create a graph, right? So we can say that a g it's going to play a similar role to the AIs of the Hamming scheme that we have seen previously. In the Hamming scheme, it's going to be a matrix, and here now it's going to be indexed by x1 all the way to some xl, comma y1 all the way to yl, and the entry is going to be the indicator. Let me shrink the size of this. So you're looking at this entry. So the xi's, they are vectors. So each one of them is a tuple in Fn to the L. And then you're simply asking whether, if you look at the configuration of their difference, x1 minus y1, etc. xl minus yl, whether this is equal to G or not with a given configuration. All right, so we have these matrices, and I think it will be interesting to see if any of those matrices that they have some nice isoperimetric properties. I don't know, right? Because yeah, and the family of these matrices here, if you look at all of them, they form the basis of an association scheme, right? Config all the valid configurations in DL. So this forms the basis of a translation scheme, an association scheme that's also a translation scheme. All right, so we have this, and it's actually a translation scheme, and the connection that Delsarte showed, this is going to tell us that if you look at a suitable theta prime of graphs that are exclusion graphs that are constructed based on this scheme, then this is equivalent to look at our LP, right? And what is the exclusion graph, right? It's very simple with the exclusion. So we need a higher order exclusion graph. So higher order, because of the hierarchy, exclusion graph. We need to forbid everything that's too close to each other, right? So I don't know here what you're going to have. You're going to have the summation of all the forbidden guys. A G, such that G belongs to the forbidden configuration. Let's have more space for forbid and DL. That set of forbidden configurations that let's work with the linear version of them. And let's call this quantity here, this is giving rise to sort of a new graph, right? And this new graph is going to be our new G and D, but now indexed by L. That's our new exclusion graph. So recall that the set of forbidden configurations is telling us when two things are too close to each other, right? All right, so we have this. It's completely analogous to the one-dimensional case. In the one-dimensional case, you're saying that we have two code words that or their distance was greater than 1, but that strictly smaller than D. And then you need to put an edge there. So here's going to be similar, right? We are looking at pairs of tuples, right? You're looking at pairs of tuples here above, right? And we are asking the question, if you compute the difference between this pair of tuples, whether it's a valid or it's a forbidden configuration or not, if it's violating minimum distance or not. So in the case of a linear code, you would have the code words of the code, right? And then you'll be computing. So this would be a tuple of code words in the linear code, another tuple of code words in the linear code. We would consider their difference, right? This would also be in the code. And you'd be asking if the span of this, the space of the difference has some violation or not. If they have some violation or not, you cannot choose both this tuple and this tuple. They cannot be both present in our code because the span of their difference is going to have a violation. So that's completely analogous to what we had before. So we have this exclusion graph, and the lemma now, and this is can be seen from a few angles again, is that the value, if you look at the value of the theta prime formulation on this graph, this exclusion graph, NDL, this is the same as the value that you get in the Krawchuk hierarchy. Krawchuk LP indexed by NDL. So it's very good. And we might have two ways of proving this. So one is via the result of Schreiber, by observing that this guy lies in the translation scheme. And the other one might be as we did in an ad hoc way, via symmetrization. So this is that this follows from Schreiber's result, if you want. Schreiber 79. But you can also think that if you symmetrize, what is the group? So we have seen that in the Hamming scheme. So for the Hamming scheme, N Hamming scheme. The automorphism that we had there was the same direct product, F2 to the n. That was the automorphism of a bunch of graphs that naturally arises in the Hamming scheme, for instance, the Boolean cube, right? And now we have this different scheme, right? That has those matrices. Potentially give a name to this scheme. Let's say that this is some NHL. That's the scheme related to these matrices here. HNL, this is the scheme spanned by those matrices. And in this new high order scheme, NL, it's our scheme. The symmetry group is going to be slightly larger. We still have the action of Sn, but then we can apply L different copies, L different translations. So we can translate the tuples independently. So it's a bit of a larger group. Okay, very good. But using the symmetry, we have seen the previous proof that if you take the matrix in the theta prime formulation, let's say that this matrix M, and if you symmetrize under the automorphism of the matrix in the scheme, you sort of project this matrix in the scheme. And once you have this projection, you can extract the variables of the LP. And the same thing happens here. So you can symmetrize under this larger group. And since the relations are transitive in the same way, you're also going to be able to obtain an LP out of that, right? And the other inequality is easier. From the LP, you can cook a feasible solution to the theta prime. So that was very quick, but it was just to say that the same relation holds, right? Same proof, you can apply the same proof to this higher order version. But that's very good because now we have a different perspective. So we have the Krochuk hierarchy, and we can sort of see this from this more intuitive formulation as an independent set problem, right, on a graph. The graph may be slightly funny, but that's okay. And what does this graph look like in our case? So if you go to the theta prime of G and D, let's try to inspect and see what's going on there. It's going to be a huge matrix, right? So huge matrix. Not possible to depict it well here, but we have this huge matrix. It's indexed by tuples of words. Very good. And then here you're going to have some entry. Very good. And this is going to be an entry that corresponds to the difference, right? It's as if we can see information related to the difference of the two. So here you have x1 minus y1, etc. So this entry is associated with this difference, xl, yl. And if the span of this part, if their span contains a light factor, non-zero factor, then this entry will be zero. Otherwise, it wouldn't be zero. But okay. And one thing that if you select a row uniformly at random here, right? This is going to be a random tuple of vectors. Suppose that we fix a column here, and we sample this guy uniformly at random, right? The distribution of the difference is going to be uniform, right? It's as if you're sampling a uniform collection of tuples. And for simplicity, let's call this Z1, although it is some ZL. So under uniform choice of a row, so sample a row uniformly. Fix a column. Sample a row uniformly. uniformly. This implies that this guy is uniform in this experiment, and it's a uniform tuple in F2 to the n raised to L, right? And what is interesting here? So suppose that you are interested in understanding this quantity here. Suppose that you're in the linear case, A2 lin ND. So it's the maximum size of a binary linear code. And let's say that this is 2 to the k0. So k0 is the optimal dimension. Optimum dimension. And for the sake of the intuition, let's say that k0 is I don't know, it's bound away from n. And what's going to happen here is that most likely when you take a collection of tuples, and if L is particularly large, right? Let's say that L is n squared or something like this. The chance that this collection of tuple spans the whole space is going to be huge, right? So you have a uniform sample here. When you look at their span, they might span the entire F2 to the n, right? And if they span the whole thing, and this case 0 is not n, it's less, then the corresponding entry is going to be 0, right? Because that will be an edge in this exclusion graph. Because an edge would see that there is a light vector here, right? A light non-zero vector, and would zero out this entry. So under this experiment, if you fix a column and you take a random row, what's happening is that we are taking this random tuple, and if the k0 that you are interested is not the full thing, and there might be a very good chance that this random tuple spans the space, you should see 0. So it means that you might be seeing a lot of zeros, right? In this experiment, there might be a lot of zeros throughout. And if you if you fix another column, similarly, there will be some different collection of zeros. So as you go higher and higher in this hierarchy, you'll see that the matrix in the theta prime becomes sparser and sparser, right? So the matrix in theta prime, let me potentially recall a little bit more the theta prime program, because could be the case that it's not as fresh. So in the theta prime formulation, we have a graph, right? So it's a theta prime of G and D, L. So this is the matrix of the theta prime that I was talking about. The objection function is the trace of J times N. Here, what we have some normalization constraint, trace of M equals to 1. Very good. So M is going to be PSD, the PSD matrix. We want all the entries UV, let's say, to be greater or equal to 0 for every choice of U and V vertices belong to V of the graph, G and DL. We need to set things to 0. So we have U, V equals to 0 whenever it's an edge in the exclusion graph. For every pair UV, that's an edge in the exclusion graph. G and D L. All right, so we have this, and recall that M is a matrix indexed by the so V by V, indexed by the vertices of the graph. All right, very good. So we have this bunch of constraints. So this is the theta prime formulation. Let's keep it here. All right. That was the theta prime. And very good. And what you're saying is that we are going to have a lot of constraints of this form now. So a bunch of a good fraction of the majority of the entries of the matrix, they're going to be constrained to be 0, right? because a typical entry in our matrix is a random tuple, and the random tuple, as provided the L is sufficiently large, is going to span the space. And if it spans the space, it has very lightweight vectors, provided this dimension is not the full dimension. Right? And we are going to take advantage of precisely that to give a bound. And we need to a few observations, right? The first thing is that we can symmetrize this matrix under the action of the group that we have. We can apply this action and assume that it's sort of in our scheme, right? And in particular, we can assume that the only thing that we're going to need in this symmetrization here is that the entries in the diagonal, they are equal to each other. That's the only thing that we're going to need from this symmetrization. So, and that's very helpful because we have this condition here enforcing the trace to be 1. And if all the diagonal entries are the same, it's going to imply that all the diagonal entries are 1 over the size, the number of vertices, right? And the number of vertices in this case is 2 to the NL, right? So a little claim here is that claim. So let's say that we are after symmetrization. Symmetrize M under the action of the group, as saying same directive to the NL. And the claim is that after the symmetrization, what we're going to get is that the diagonal entries are the same. So MU is equal to MVV for every choice of vertices. U and V belong to the vertex set. And we, from the constraint, that trace of M is equal to 1, it follows that that MUU is 1 over the number of vertices, which happens to be the number of L tuples of binary vectors of length n. So this is precisely this for every diagonal entry. And the matrix is PSD. And if you have a diagonal entry of this form, we cannot have an off-diagonal entry that's larger than this. It would violate PSDness. Since we have a PSD, we get that the off-diagonal entries, UV now, in absolute value, they are bounded again by 1 over 2 to the NL for every UV. Otherwise, it would violate PSDness. And that's definitely something that we want to store here. So you're saying that the L infinite norm of this matrix, let's record this in the claim. After symmetrization, we get that the infinite norm, the largest entry, is bounded by this much 2 to the NL. Now let's continue with the strategy, and the strategy should count the number of non-zero entries of M. And use this bound and multiply by the infinite norm. So it's a very, very simple strategy, and that's going to give, let's call it the number of non-zero entries. Let's give a name to this. Let's say that this is some, I don't know, some quantity p. You're sort of saying that the objective function Jm is going to be bounded by this quantity p times the infinity norm. All right, and now let's, so this is the objective value of the theta prime. So recall that the objective value of the theta prime is precisely this. So we'll be giving an upper bound. And how do you count P? So it's not hard. How do we count P? How do we count the number of non-zero entries? The simple observation is that whenever it's going to be easier. So first, let's not count directly the number of entries, but let's rather count the number of tuples Z1 all the way to ZL that are non-zero. So you're not going to count. Let's see if I have here. So let's not count the number of entries like this that are non-zero, but rather let's look at already the difference here and understand if they're going to lead to something that's non-zero, right? Because this given difference, this particular choice of Z1 all the way to ZL, we can generate it in 2 to the n times L of forms, right? So whenever we have a given Z, we can generate this as some x1, you take an arbitrary guy like this, xl, and it's generated in this form, x1 plus z1. So you're in f2, plus and minus, they do not matter, plus zl. So we are going to have a bunch of tuples such that the difference, their difference generates this guy. So we can freely choose among the 2 to the NL choices, right? And their difference is going to generate this tuple. So it's enough for us to just focus on the difference, right? And then count how many tuples, L tuples, can be non-zero, right? And then multiply this by 2 to the NL. I think it may have been a little bit slightly confusing, but I'm going to clarify it later. Let's just focus on this difference here and see how many can be non-zero. And the observation is that you can look at the span, right? Span of Z1 all the way to ZL. And we know that the best code, has mentioned the best code that still satisfies the minimum distance has dimension K0. So if the dimension of this space happens to be larger than K0, we know that's going to be 0. Right? If the dimension of this happens to be larger than K0, then the corresponding entry is going to be forced to be 0. So it's enough to consider only spaces that have dimension at most K0. And very good. So we only need to consider this. And for simplicity, let's start with the case that the dimension is precisely K0. And let's count how many such tuples we can have. Right? It's an easy computation. And the number of such tuples is going to be, let's call this, you're counting the number of tuples that's going to span a space of dimension K0. And that's not too bad, right? You're going to choose K positions, out of the L positions, you're going to choose K0 positions to place a basis, an ordered basis. Place an ordered basis. We are choosing the positions in the tuple. And how many ordered bases we have? Let's give an easy upper bound. So this, everything here is going to be an upper bound. So this is going to be K0 times n. Very good. So with this, we looked at this L tuple. We chose K0 positions to put a basis for this K0 dimensional space. How many K0 dimensional spaces we have? This is an upper bound because you can think that a binary matrix of these dimensions, right? K0, so matrix in F2 to the n, whose columns are linearly independent, will define a space, right? But you're counting all of them, right? So you're potentially overshooting here a little bit, but that's going to be okay. And very good. But we are left with L minus K0 positions that we haven't said how to fill them. But if you want to keep the dimension to be at most K0, they need to be in the span or in this space, right? In this K0 dimension space. Or otherwise it would increase the dimension. So you're saying that for every subsequent element here, what you're going to do, we have 2 to the K0 vectors in that space, right? Because that's the dimension of the space. And then we are going to, for each of the L minus K0 positions, we are going to choose one vector in this space. So let's recap. First, in this tuple, we choose K0 positions to place a basis of a vector space of dimension K0. Then we choose one such space that's an upper bound on that. And for each of the remaining positions here, we cannot choose a vector that's outside that space. So we choose vectors that are inside the space, and we get this quantity here. We get 2 to the K0, right? And we raise this to this number of times. Very good. So we have this upper bound, and this was for the dimension precisely K0. But let's massage this expression a little further. So an upper bound on this would be L to the K0, 2 to the K0 times n, and 2 to the K0 times L. Very good. And this is a growing function on K0, right? It's definitely growing on K0. So what you can do, instead of analyzing, I don't know, dimension 0, 1, all the way to the K0, in the total count that you're going to have, it suffices to multiply this by, let's say, n plus 1. Right? You need to consider all smaller dimensions, but it would be enough to just overshoot and say that we are summing this much. And this looks a bit promising, right? Because our hierarchy is meant to get the size of the code, right? The size of the largest code, which is this part, raised to the L, right? And that's getting here, right? And the bound that you're going to deduce comes from taking the L chief root on the above expression, right? So taking the L chief root, we see that things are going to be nice, right? So if you consider the limit of L going to infinity, if you're taking the hierarchy to the extreme, you're going to get a leading to the K0. So this comes from this part here. Very nice. It gives us this. And all the other terms, you're going to have a root, right? An L chief root. N plus 1 times L K0, 2 to the K0 times N. And it's clear that this part here is going to 1, right? As L goes to infinity. Right? So this part doesn't depend on L at all. This part does not depend on L at all. And this part that depends on L, it depends mildly, right? So the root is shrinking this quantity much faster. So at the end of the day, the limit of this quantity is 2 to the K0. And that was a crude bound, that was just showing that in the limit you get what you want, but it's very simple to see that if you choose L to be, I'm even overshooting this a bit, it should just be something about n squared, you might get something very close to what you want, right? Because you need the hard part to beat is this part here, this K0 times n. K0 could be somewhat linear, right? And then you have this 2 to the n squared here. So that's why we need level, at least in this very nice form, we may need level all the way to n squared. All right, so that's yeah, that. So I jump one step here. So let me back. So I said that it was okay to focus on the Z and not consider the pairs like this. And it was okay because a Z can arise in how many ways? In 2 to the NL ways. But the 2 to the NL ways is going to cancel with the bound, the infinite norm bound that we have in the matrix. And the infinite bound norm that we have in the matrix is as we have shown, right? It's 1 over 2 to the NL. So it cancels perfectly. So the number of pairs, 2 to the NL, cancels with the infinity bound. So in discount this part, so there is an extra 2 to the NL that cancels here because of this infinity bound. And that was sufficient to. So then it was enough to count the octuples, and that was precisely what we did. We give an upper bound and show that it converges precisely to the K0. And 2 to the K0 was by definition the A2 lim MD. It was the optimal size of a binary linear code of block length n and distance t. And a more careful analysis shows that completeness happens at level about n squared. All right. So it's potentially a little bit technical, the proof, right? It requires some computation. It's not very hard, right? And what was crucial was this equivalent perspective that we have in the hierarchy. So it took us about 1 year just to see this completeness proof. We had the hierarchy for some time. And it was only thanks to this different perspective, this theta prime equivalence that's more intuitive, that you could see that some of the entries in the matrix, they should become 0, and that was something that one could explore to potentially give a completeness argument. Right? That's precisely what happened. All right, so let's summarize and then wrap up this part. So we just proved, or better, sketched. So we have just sketched this completeness proof. And now it seems that, because it's a bit strange, right? Our hierarchy is not as sophisticated as a general purpose hierarchy, like sum of squares and so on, right? So it made the completeness proof a little bit unusual, right? In those other hierarchies, you have more structure to do the rounding and so on. Here we had less structure, right? And the natural question was that it feels somehow that level about n should be the correct answer, because at level n you should be seeing an arbitrary span, right? You should be able to understand linear subspaces very well. And it seems that now we may have a proof of exact completeness at level L, right? But it requires further checking and verification. So I'm not going to present this, but it's good that potentially now we may have some exact completeness at level N. And the challenging question is whether you can take advantage of this hierarchy. Can we somehow use the techniques available or enhance them to be able to tackle this hierarchy and squeeze better bounds out of this? So that's the interesting question that we leave. And one thing that we did not cover is this collapse. And if someone tells you that there should be a collapse, it's not too hard to prove. And again, the collapse is using the theta prime formulation. It's much easier to see from the theta prime than seeing from this LP. So this LP is very good because it resembles a lot Delsarte's LP and so on. But it's curious that the theta prime it gives a very intuitive perspective that you can derive these other results. All right, so I'm going to stop here. I hope it was sufficiently clear, the completeness proof, and thank you very much for your attention. And stop here.